Hi everyone, welcome to the Renewable Integration Study webinar on Technical Appendix C, Variability and Uncertainty. So this recording is intended to provide a summary of the key findings and actions that come out of the Variability and Uncertainty Technical Appendix. So today we're down here in the red highlight. As you can see, there are 5 recordings that we've done to cover off a technical and non-technical overview of the RIS, as well as summaries of all of the technical appendices. So if you haven't already, I recommend that you check them out on the AEMO website on the major publications page. So the full RIS report and appendices can also be found at this location on the AEMO website. So chatting with you today is me, Eloise Taylor, along with my colleague Quinn Patterson. So we are both members of the Future Energy Systems team at AEMO and have been working closely with the technical RIS studies over the past year. I was also the stream lead for the variability and uncertainty analysis in the RIS, which we'll be covering off today. In today's webinar, Quinn and I are going to be looking at 4 things with you. Firstly, the key concepts that we need to understand before delving into all of the analytical detail. Secondly, we're going to look at our approach to scoping this study. Thirdly, we're going to cover off the 4 core areas of analysis for this appendix report. And lastly, we're going to have a look at the high-level outcomes for this variability and uncertainty work. So I'm now going to hand over to Quinn to take us through some of the basics so that we're all on the same page.
Thanks, Eloise. Okay, so let's get started. The power system is a huge and complex machine. One of the sources of this complexity is that the supply and demand for electricity must be balanced continuously and instantaneously. This is really important in any power system, as electricity is not a readily storable commodity, although we do have some limited pumped hydro and battery storage facilities in Australia. So why is this balance important? Well, the grid is designed to operate at a certain frequency. In Australia, it's 50 Hz. Maintaining frequency is done by balancing supply and demand at all times. If we deviate too far from this 50 Hz mark, it can cause damage to equipment, or the equipment may disconnect, which may cause further imbalance. In understanding this balance, we need to also understand these concepts of variability and uncertainty, which make balancing supply and demand harder. Variability is the movement up and down in both demand and supply that would exist even with perfect foresight. And uncertainty is the inability to perfectly predict future demand, supply, and grid conditions. Now, both demand and supply have always been variable and uncertain. For example, demand varies on daily and seasonal cycles. Similarly, for uncertainty, there have always been unexpected events, say an unexpected line outage, which also takes out some generation. And our forecasts have always been just forecasts. They're not always 100% on the money. In this new sort of world that we're moving into, we're experiencing ever-increasing amounts of variability and uncertainty, mainly due to increases in utility-scale wind and solar and in distributed PV. On the right here, we have an example of variability and uncertainty from an individual utility-scale solar farm over a single day. The red line shows the actual output for the day, and the purple line shows the forecast 12 hours ahead. You can see a couple of kinds of variability happening here. Firstly, the purple forecast line and the red actual line both show the diurnal pattern that solar takes over the course of the day, from the rising and the setting of the sun. The purple forecast line and red actual line are close together, indicating that these periods were reasonably well forecast. Secondly, you can see that there was quite a bit of variability, especially in the middle of the day. So you see power going very low for this individual site, and then rebounding very quickly, perhaps due to some cloudy weather. The output resulting from this weather phenomenon is more uncertain. You can see that the forecast did not pick up these deviations very well. Why is this important? Well, because the balancing of the power system occurs at a number of different timescales. To balance the system, operators must have information about the level of uncertainty in their forecasts, as well as the capability of their resources to respond. Forecast accuracy increases closer to real time, but the ability to respond to unexpected events decreases because the operating range of conventional power plants is smaller over shorter time intervals. This problem is magnified by the challenges of generator scheduling, because thermal generators typically require significant lead time, hours to days or even weeks, to be turned on or off. Over these longer durations from weeks to days ahead, AEMO has a process called the Projected Assessment of System Adequacy, or PASA for short. At a high level, these tools are assessing whether there's likely to be enough supply to meet demand at these times. While all plants across the NEM need to submit their availabilities as inputs to these processes, the PASA process is not binding and instructions to generate or hold reserve are not determined by a market mechanism over these periods. Over this sort of time frame, we, as the system operator, would get a good feel for what thermal generators are going to be online for the projected period. Also at this time frame, we as the operator can activate out-of-market responses, such as the Reliability and Energy Reserve Trader, or RERT, and issue directions and instructions if the reserve levels fall below acceptable thresholds. As we get closer to real time, the demand forecast improves, and there's a much clearer picture of unit commitment and pricing intentions. Every 5 minutes, AEMO runs a security-constrained economic dispatch process. This is where online units are given energy targets to meet based on the 5-minute ahead forecast, subject to a range of constraints. In this time frame, you might also be able to start up some fast start units or batteries as well. Now, even with the 5-minute intervals, there's still more variability and uncertainty to account for in the supply-demand balance. We deal with fluctuations at this timescale using the Regulation, Frequency Control, Ancillary Services markets, or FCAS. On the second to minute timescale, we also have contingency FCAS markets to deal with larger sudden deviations. For more information on frequency, have a look at our Managing Frequency webinar. So what this tells us is that flexibility is key to balancing the system over different timescales. This system flexibility concept is the capability of the system to respond to expected and unexpected changes in supply and demand over all necessary timeframes. You can see that it's important to know what is turned on and to be able to ensure that we have the right resource mix when we need it to maintain the supply-demand balance. Okay, so that's our core concepts done and dusted. Now on to the approach we took to this study. In essence, we did a huge piece of data analysis looking at how this variability and uncertainty is changing out to 2025, and a high-level analysis on the system's capability to accommodate this increase. The analysis was scoped into 4 stages, which you'll see on the screen. Each subsequent piece builds upon the previous to help interrogate the data from different angles and develop a clearer picture of the limits that variability and uncertainty may pose to the system. Okay, I'll pass back to Eloise now to take us through the first few areas of the core analysis.
Thanks, Quinn. Let's move straight into the first area of analysis, which was generation variability. From this piece of analysis, we really wanted to understand how much variability from VRE, so that's variable renewable energy, is expected to change out to 2025. So we're essentially interested in variability from utility wind, utility solar, and distributed PV. We analysed a 5-minute resolution dataset covering a 4-year historic period and also a future synthetic year. So it's important to note here that each ramp was taken as the megawatt difference between the start and the end of an interval, so the difference between 2 instantaneous points. The analysis in the report covers ramps over 5-minute, 1-hour, and 4-hour overlapping intervals. So by overlapping intervals, I'll give you an example. For 1-hour ramps, we might assess the change in megawatts between 9 and 10 a.m. in the morning, and then between 9:05 and 10:05, then 9:10 and 10:10, and so on and so forth. So a 1-hour interval shifted every 5 minutes. The key graphic coming out of this generation variability analysis we've endearingly called the butterfly plot, which we've got up on the screen here. Now, these butterfly plots show the monthly 99 percentile 1-hour ramp between 2015 and 2019, and then projected forward to 2025. So these are the values that are exceeded in only 1% of cases. Putting this into a bit of context for you, the top 1% of hourly ramps in a year, by our methods, would be roughly the top 1,000 ramps. And in a month, this is roughly the top 80 to 85 hourly ramps. Now, before we get into what we can learn from this graph, let's take a quick look at how to read it. So we've just focused in here on the NEM panel for simplicity, and there are 2 key components of this panel that we need to focus on. The first are the coloured bars, so the purple, the red, and the orange. These show the monthly 99th percentile ramp that's observed in each region for wind, utility solar, and distributed PV individually. Now, the largest 1% ramp for each of these three technologies is really unlikely to occur at the same time. So, stacked together, they represent the top 1% theoretical ramp for a region if all VRE types had their 99th percentile ramp simultaneously. Now, the white line, well, that's the observed monthly 99 percentile ramp that resulted from the overall movement in wind, utility solar, and distributed PV. So this line shows what was actually observed in the month. Okay, so back to looking at all of the regions together. Now, there are two key takeaways that I want you to get from this graph. The first is that the size of VRE ramps is growing out to 2025. So these upward and downward movements are getting a whole lot larger. In the NEM, the largest historic 1% downward VRE ramp over an hour was 1.4 gigawatts. However, this is projected to reach 4.5 gigawatts by 2025. This is a jump of more than 50%. The second thing is that diversity is important. So, although the ramps are increasing in magnitude, these increases are smaller compared to the growth in installed capacity. What we see on the graph here is as we move from 2015 through to 2025, there's an increase in the observed 99th percentile ramp in the region, which is the white line trending up. However, this increase is not proportional to the growth in the theoretical maximum ramp, so the increase in the stacked coloured bars. So, the more diversity of technology in a region, the larger this gap. So from the graph in front of you, we can see that Victoria seems to have the most diversity in VRE technologies by 2025, with the most equal projected ramps from each technology type, so the most equal looking coloured bars, and also the largest difference between the net ramp, so that white line, and the theoretical top 1% ramp. The appendix report also looks at geographic diversity, but I won't dwell on that now. So for more information on that one, you're going to have to check out section C3.3 of the report. Just looking at variability from VRE is interesting, but it doesn't tell us the whole picture about the system. So the next step for us was to incorporate variability from underlying demand with variability from VRE. This is a concept we call net demand in the report. It gives us an idea of the residual variability that would need to be covered by the scheduled fleet in the NEM. The way we've assessed this also assumes that the aim is to allow full utilisation of wind and solar farms that are being built across the NEM out to 2025. So if the wind and solar have energy available, it's assumed to be used in the system. For this component of the analysis, we moved away from the 5-minute resolution onto a 30-minute resolution due to the availability of demand data for the synthetic year. We've also looked at the 1-hour and 4-hour ramps in an overlapping fashion. This is the same concept I described before for the generation variability. This graph here is one of the main ones we have in the net demand section. Each one of the dots here shows the hourly change in net demand at a 30-minute resolution, and the different colours represent the different seasons throughout the year. So we want to understand for every hour window in the year, so for 2018 on the left and 2025 on the right, how much VRE was moving, and also how much underlying demand was moving. And this is because the combination of the two make up net demand. Now, there's a lot of information tucked into these graphs, but it's worth it. So we're going to unpack it a little bit over the next couple of slides. Okay, so we've mapped underlying demand here on the x-axis down the bottom and VRE ramps on the y-axis on the side. You can also see that the movements in both VRE and underlying demand can be up or down. We've just popped some symbols here to show this a bit more clearly. Now, based on this division, we can then go and divide the graph into quarters. So quarter 2 and quarter 4, which are highlighted here, show hourly intervals where VRE and underlying demand moved in the same direction. So when they move in the same direction, they are offsetting one another. Now, when VRE and underlying demand movements are equal and in the same direction, they offset one another entirely. So in these instances, a movement up or down in underlying demand would be completely serviced by the same movement up or down in VRE. And the scheduled fleet could just essentially sit pretty and not move at all. This is a net demand ramp of 0 and is shown here by the black dotted line. The other quarters, quarter 1 and quarter 3, show instances where VRE and underlying demand moved in the opposite direction. When they do this, their movements exacerbate net demand requirements, so the scheduled fleet needs to work a whole lot harder. The last thing we need to understand are the blue and green lines. We already understand that the black line here is where the net demand ramp is 0. Now, the blue and green lines follow the exact same concept, except they show when net demand ramp is plus or minus 3 and 5 gigawatts. So the green dotted line shows plus or minus 3 gigawatt net demand ramp, and the blue dotted line shows a plus or minus 5 gigawatt net demand ramp. So to make things even clearer, anywhere that's shaded here in the grey region is an hourly net demand ramp of between 0 and 3 gigawatts. Anything in the green shaded region is between 3 and 5 gigawatts, and anything in the blue is a greater than 5 gigawatt net demand ramp. Okay, let's go back to our main graphic to see what it actually shows us. In the RIS main report, we made a few high-level remarks about the changes in net demand, and many of them can actually be understood from this single graph. So firstly, the magnitude of 1 hour net demand ramps is increasing. You can see as we move from 2018 on the left to 2025 on the right, there is effectively a big dot explosion on the page. Importantly, the dots are moving beyond these 3 and 5 gigawatt lines we looked at previously. You can see that we've highlighted the greater than 3 gigawatt region in a dark grey, and this is because this is the most challenging region. It is where the scheduled fleet needs to ramp up to cover this increase in underlying demand and decrease in supply, which can be particularly challenging in situations where there is a limited available capacity of online generation or upward flexibility available on our interconnector. But more on that later. We'll get Quinn to cover that for you. Second, VRE will be a significant driver of net demand by 2025. This is evident by the change in shape between 2018 and 2025. Okay, so let's focus on the grey double-headed arrows first. In 2018, the grey arrow is bigger than the black arrow. Now, this tells us that in 2018, underlying demand was a key driver of net demand movements. However, between 2018 and 2025, the grey arrow doesn't really change in size. So the range of hourly underlying demand ramps are not really changing a whole lot between these years. Now look at the black arrows. There is a big change between 2018 and 2025. There is a huge growth in VRE movements. Now, we learnt that from the butterfly plots already. But what's more interesting, in 2025, that black arrow is now also a lot larger relative to the grey arrow. So VRE has outpaced underlying demand in terms of driving the needs for movements in the scheduled fleet. On to the third building block. So now that we understand variability a bit more, and we know that VRE is going to be the big driver of net demand ramps by 2025, the next step was to understand how well we can predict these fluctuations. So if we can predict ramps well, then it's easier for participants and us as operators to ensure that the right resources are available to manage ramps. If we can't predict them well, then we need to ask ourselves if our current tools will be fit for purpose going forward. For this analysis, we compiled a new dataset of forecast accuracy measures for 2018 only. This was across all large-scale wind farms and solar farms, so no distributed PV. The information we compiled was from AEMO's dispatch, 5-minute pre-dispatch, and pre-dispatch processes. Okay, so we might use a bit of a case study to take a look at how we assessed uncertainty for this report. What we are looking at here is a graph showing wind output in South Australia on the 18th of December 2017. We can see the 1 hour ahead, 8 hour ahead, and 24 hour ahead forecasts, as well as the actual output on the graph. We can also see that in the morning there's not a lot of variability, and most of the forecasts seem to be doing pretty well. The 24 hour ahead is undershooting a little bit, but is corrected by the 8 hour ahead. By contrast, what we see in the afternoon is that there is a lot more variability. Now, this variability came from a wind change due to a large low pressure system that moved east across South Australia during the day. So you can see here as well that there are some differences in how variability was captured between the 24 and 8 hour ahead forecasts compared to the 1 hour ahead forecast. But before getting into some of the reasons that these forecasts look like they do and the challenges of forecasting, I'd just note that the technological development and innovation over the last 20 years has resulted in some significant improvements in weather and power forecasting accuracy, with advances in computing power, sensing equipment, data processing, and so on. I'd also point out rather obviously that a forecast is always going to be a forecast and that there are also limits to how good they can get. Now, let's have a look at the 24-hour and 8 hour ahead forecasts compared to the actuals. So the 24-hour and 8 hours you can see here showed minimal predictions of this ramping event in the afternoon. Now, these types of forecasts over longer lead times rely on global numerical weather prediction models, or NWP models for short. Essentially, these models have long lead times in the ingestion of weather observations and also long periods between model reruns. This means that if weather systems are developing faster or slower than the model predicts, such as a low pressure system moving through a state, this might not be picked up for some time. Also, during this particular ramp event, the local effects of the prefrontal trough and a large band of precipitation weren't well resolved by the NWP model. Now, these are all commonly known challenges for these sort of models. On to the 1 hour forecasts. We can see that this forecast looks like it is lagging behind the actual generation throughout the day. So when the actuals move up or down, the forecast seems to do the same an hour later. Now, this is because the forecasts closer to real time rely on a mix of persistence and real time SCADA data. So while forecasts improve closer to real time as more up-to-date information is incorporated from SCADA, the persistence component of these forecasts mean they tend to say what is happening now will continue to happen in the future, and as such, they lag actual real-time generation. Now, how did we actually assess uncertainty in the report? Well, we used two measures, point forecast error and ramp forecast error. Currently, AEMO's forecasting models for wind and solar energy provide what we call point forecasts. So these are deterministic, which means they give an estimate of exactly what they think the output of a farm will be sometime in the future. They are not probabilistic and they do not explicitly account for uncertainty of forecast conditions. So let's zoom in on this case study figure we've been looking at a point where there's a little bit of variability. Now, starting with the point forecast error. So this is calculated as the difference between two single points. Let's take the 8 hour ahead point forecast error for 2300. The 8 hour ahead forecast was for 891 megawatts, but what actually transpired at that time was an output of 1194 megawatts. So we under forecast by 303. Easy, right? Now, we wanted to assess our wind and solar forecasts on their ability to predict upcoming variability rather than output. This is kind of like judging a moped on its ability to carry a piano. It's not fit for purpose. This is not what we designed our forecasts to do. However, it does allow us to judge the tools we currently have on their ability to provide information that we believe we will need to operate the system in a high VRE future. To measure the ramp forecast accuracy, we need to compare the change between 2 points for the actual and the forecast. So let's take the 8 hour ahead forecast between 2200 and 2300. So we calculated that 8 hours ahead, the hourly ramp would be 2 megawatts. However, in actual fact, it turned out to be 701 megawatts up. So the actual ramp was 699 megawatts larger than we forecast over that time. Now, if we do these types of calculations more broadly across the whole 2018 dataset, what we found was that the point forecast accuracy generally improves closer to real time, but the ramp forecast accuracy actually gets no better. So while we do get better at predicting output the closer to real time we get, which is what our models are built to do, we get no better at predicting variability. The analysis shows that there are limitations to how accurately we can predict variability, and the current tools need to be adapted to help quantify this uncertainty. I'll now hand back to Quinn to cover off the last building block for this analysis.
Thanks, Eloise. Now we come to building block 4, our final building block, system flexibility. Now that we have a good understanding of wind and solar-driven variability and uncertainty, the last question becomes, how will the system need to behave to fully utilize wind and solar resources? The capability of the system to respond to net demand variability and uncertainty over all necessary timeframes is called flexibility. As the system moves to higher penetrations of VRE, there's likely to be a level of VRE curtailment that's determined by the market as it relates to participant risk and also to risks to system security. What we tried to do with this analysis was to look at the ability of the system to act flexibly to fully utilize all the VRE that's planned to come into the NEM out to 2025. In this sense, we're looking at the physical system limits rather than trying to agonize over what the market will deliver by 2025. In this analysis, we took the draft 2020 ISP Plexos modeling outputs and did some post-processing to give some insight on future system flexibility. There's a range of inputs and assumptions for this model, which differ from that of the ISP, and these are all listed in section C7.2 of the report. To understand how the system will behave in the future and whether we'll have enough system flexibility to cover increases in variability and uncertainty, a good first step is to understand what resources are expected to be available and any big changes to the makeup of the grid. So we can see here that the flexible attributes of the system are changing out to 2025. For example, there's more VRE, less coal and gas through retirements and displacement of online resources, and there's more interconnection. Sources of flexibility considered in this analysis include headroom on conventional units, battery storage, fast start units, and interconnection. It is also expected that additional sources of flexibility may play a role by 2025, such as an increase in demand response, pre-curtailment of renewables, virtual power plants, and so on. These sources should also be considered and modeled to a greater depth than done here, as these processes or technologies mature going forward. Some of the analysis of our modeling is presented here, with regional flexibility plots for 4-hour windows. Our analysis included flexibility over both 30-minute and 1-hour windows too, which can be found in sections C5.2.2 and C5.2.3 of the report. These plots here show the number of challenging days each NEM mainland region faces under different sensitivities. A challenging day is a day where our modeling identified a negative ramping margin, which is when there's not enough flexibility under the given sensitivity to meet an upward ramp in net demand, in this case, a 4-hour ramp. These challenging days represent periods where the demand and supply for flexibility is tight. Under these conditions, both participants and operators need to manage these ramping margins to ensure the system is secure, assuming we're trying to accommodate full utilization of the VRE fleet in 2025. The next slide shows how to interpret the different sensitivities explored over 4-hour windows. Ramping assessment was completed on a region-by-region level, as shown in the orange highlight. A number of sensitivities are covered off in these graphics. The sensitivity studied for 30-minute, 1-hour, and 4-hour ramping windows were all different. We're only looking here at those for the 4-hour ramping windows. I'll take you through them all now. The first sensitivity is VRE ramp uncertainty, highlighted here in purple. VRE ramp uncertainty looks at the extra flexibility that would be required to meet a ramp in net demand that was 10% to 30% higher than the system was dispatched to meet. Second, we have the status of the offline slow start fleet, highlighted there on the left. How long each unit takes to start up is affected by the unit's specific design and how long it's been offline and allowed to cool down. Participants must anticipate when they need their units to be online in accordance with the market conditions and their portfolio position, and will manage their units to meet their business needs. Forecasting this behavior is pretty complex a day ahead, let alone 5 years ahead, so we've left it out of the scope of this analysis. Instead, we speak to this by considering the difference in flexibility that would come from a unit being allowed to cool with no active management versus the extra flexibility that would come from participants ensuring that their units are at least warm or are all hot in the lead up to each 4-hour ramp. Lastly, interconnector availability is our final sensitivity, highlighted in dark red. Interconnector availability is an outcome of market conditions, which, as we've just said, are difficult to forecast and are outside the scope of our analysis. As interconnection plays a significant role in the flexibility of every region, it's important to consider the effect of low, medium, and high interconnector import availability. Low, medium, and high import headroom are represented by the 10th, 50th, and 90th percentiles of modelled import limits into each region. Now, we arrive at key insights from 4-hour plots. This graph is a litmus test for challenges managing net demand ramps in each region. Rather than focusing on the size of the number, more attention should be paid to what aspects each region is most sensitive to. Both Queensland and South Australia may face the highest number of challenging days if offline slow start units are unavailable at times of low interconnection. Detailed discussion of these conditions under these sensitivities and over 30-minute and 1-hour ramping windows, they can all be found in the report in section C 5.2. So, we arrive at our summary for flexibility. This graphic we've got here on the right summarizes the key insights from our flexibility analysis for each region. Firstly, the drivers behind the supply of flexibility are specific to the ramping window, region, and market behavior. The intersection of these different aspects gives a wide range of circumstances in which there may be a great amount of flexibility or not much at all. For example, we've just looked at 4-hour windows, over which we saw the interconnector headroom and the status of offline slow start plant has a large impact on system flexibility. On the other hand, when we looked at 30-minute windows, we found that net demand ramps over this time frame are most sensitive to the response of fast start units. The results of this study must be considered in the context of its limitations and assumptions. Our analysis doesn't aim to give a quantitative statement on when risks may emerge, but instead it gives a relative view of factors which may have a high impact on flexibility under high penetrations of wind and solar. What our analysis does show is that a range of flexible resources must be utilized and planned ahead of time. Adequate market signals are needed to encourage local flexibility when required, and identifying challenges managing the most extreme net demand ramps with available resources is highly sensitive to the assumptions underlying the analysis. As the market's collective experience operating with increasing levels of wind and solar increases, a clear picture of what flexibility is available to the system may emerge. When you put all that together within the bounds of this analysis, we found that full utilisation of wind and solar has the largest impact on system flexibility in South Australia and Queensland. This is based on the number of challenging days in each region assessed over all sensitivities and all timeframes. Okay, now over to Eloise to wrap up the presentation.
Thanks, Quinn. So, what have we learnt from this analysis and where is it taking us? Well, we've learnt that the size of VRE ramps is increasing at a serious rate. The magnitude of peak VRE ramps is forecast to increase by 50% out to 2025. We've learnt that the movements in VRE will become the main driver of net demand ramps, which define the requirements on the scheduled fleet. We know that both supply and demand are becoming harder to predict. There is more uncertainty out to 2025. And this all leads us to an increasing demand for system flexibility. Now, this system flexibility needs to be harnessed in all parts of the power system, and these resources need to be utilised and planned ahead of time. So, essentially, to manage these challenges we're faced with, we either need to decrease uncertainty in the system or increase flexibility, or a little bit of both. And to do this, we need enhancements to our operational tools and processes and regulatory frameworks to support this change. So, what are these operational tools and processes and regulatory frameworks? Well, these are the 4 recommendations coming out of this work, and they are also outlined in section C6 of Appendix C and also in the RIS main report. You'll notice that recommendations 2.2 and 2.3 here are bracketed, and this is just because these recommendations are shared with the operability section of the report. So really, the actions coming out of this work are that we need to adapt the forecasting systems that we have to improve our understanding of uncertainty and risk, particularly during ramp events. We also need to redevelop existing scheduling systems, like our PASA system, to better account for system needs such as ramping requirements. Third here, we need to improve the information that is provided into these scheduling systems in order to have the right resources available at the right time to manage future variability and uncertainty. Action 2.3 here is pointing towards the work being carried out by the Energy Security Board post-2025 market work. This work is investigating the valuing of essential system services such as flexibility and also the right mechanisms to ensure that the right resources are available at the right time. Okay, so finally, tying this back into the broader RIS landscape. Some of you might remember this chart from the technical overview webinar. If not, that webinar goes into the understanding of this graphic in detail and is available on the AEMO website. So this shows a view of the instantaneous penetration of wind and solar generation as a proportion of underlying demand, with each coloured dot representing a single half-hour period within a year. So we've also progressively overlaid the system limits and challenges depicted by each of the coloured zones, and when actions from each of the key RIS areas is needed to begin. So of importance here in the light blue, we see the challenges with managing variability and uncertainty, which need consideration for wind and solar penetrations above 50%. So this is what's related to this appendix. So given the lead time on many of these actions, so actions from variability and uncertainty, system strength, frequency, distributed PV, and operability, our recommendation in the report is that all actions, including the ones I just took you through on the previous slide, need to commence immediately in order to have them in place in time to support the ongoing system transition. In combination, if all of these actions are taken, we think it could be feasible to operate the NEM with instantaneous penetrations of wind and solar generation of up to 75% by 2025. So that's the black line you see here in this graph. However, if these actions aren't taken, we'd expect the various system limits would cap wind and solar penetration levels at between 50 and 60% of total generation. Looking to the future, AEMO has not actually identified any insurmountable reasons why the NEM can't operate securely into the grey zone, so above 75%, with instantaneous wind and solar penetrations potentially reaching up to 100%. So, that's it for this webinar on the RIS Technical Appendix C, Variability Uncertainty. Thanks for joining Quinn and I. Just a reminder that for an overview of the RIS or to delve into other technical appendices, head to AEMO's website to check out the rest of the series. Until next time.